Ever wondered how engineers design something truly massive, like the world's tallest skyscraper?
Making sure it stands firm against, hurricane winds.
Exactly. Or maybe something complex, like a deep-sea submersible, right?
Yeah.
Guaranteeing it withstands those crushing pressures down there.
Yeah, it's definitely far from just guesswork.
It really is. It's about knowing precisely where weight acts, how various forces distribute themselves across a structure.
Mm-hmm.
So today we're taking a deep dive into some really fundamental concepts in mechanics. We're talking center of gravity, center of mass, and the centroid.
These are kind of the invisible balance points, you could say. They dictate how objects behave.
How they're built, how they react to everything around them.
Yeah, absolutely. And we've been working through this really fascinating chapter from a foundational textbook. It meticulously breaks down these ideas.
Right.
And it doesn't just tell us what these points are. It actually reveals the powerful methods engineers use to calculate them.
Okay, so our mission here in this deep dive is to maybe cut through some of the complex equations you might find.
Mm-hmm. Distill the core ideas.
Yeah, distill the key insights so you can understand what these points are, why they are just absolutely essential in design.
And how they really empower engineers to build everything from, an everyday chair
to the most advanced spacecraft.
Yeah.
It's kind of your shortcut, maybe, to being well-informed about this crucial concept of an object's and a force's balance point.
Definitely.
All right, let's start maybe by clarifying the fundamental distinctions, because these terms, well, they often get used interchangeably.
They do, and they really shouldn't be.
Okay, so first up, the center of gravity, G.
Right. G. This is that single unique point where effectively the entire weight of a body can be considered concentrated.
Okay. Like, imagine trying to perfectly balance an irregularly shaped object. Maybe a piece of driftwood you found.
Yeah, good example.
On your finger. That delicate balance point, that's its center of gravity.
Exactly. And this point is crucial because it tells us where the total gravitational force, the weight, effectively acts on the body. It's really the combined effect of, countless tiny weight particles that make up the object.
Right. The sum of all the parts.
Precisely. And for most practical engineering applications, here on Earth, we usually assume a uniform gravitational field.
Meaning gravity is pretty much the same strength and direction everywhere nearby.
Yeah, basically.
Okay. Now, a very close cousin, and one that often gets confused with the center of gravity, is the center of mass, C.
CM. Now, if that gravitational field we just mentioned is perfectly constant and uniform,
which we often assume.
Right. Then these 2 points, G and CM, are actually the same point.
Okay.
But the center of mass becomes particularly important when we're studying the dynamic response.
Like things moving, accelerated motion.
Exactly. Think about how a rocket accelerates into space, or maybe how a race car handles a high-speed turn. It's really about the inertia of the object, its mass distribution. Got it. Okay, dynamics versus statics, kind of.
In a way, yes.
And finally, we have the centroid, C.
C. This one's purely the geometric center of a body.
Geometric center, meaning?
It's defined by its shape alone. Doesn't matter what it's made of. Whether that shape is just a line, like a thin rod, or a flat area, or a 3D volume.
Just the pure geometry.
Pure geometry.
Now, you mentioned these points. G, C, M, and C are often the same.
Right.
But you hinted they aren't always.
Correct.
Can you give us an example where they're different and why that difference becomes, absolutely critical for engineers?
Yeah, that's a great question. And it's really where the precision of engineering comes into play. So the centroid, the center of mass, and the center of gravity, they all coincide. They're the same point, only if the material making up the body is uniform.
Homogeneous.
Homogeneous, exactly. Meaning the density is the same throughout.
Okay.
Otherwise, they absolutely can be different points. Imagine you're designing, say, a part for a new drone.
Right. Lightweight is key. Exactly. So maybe you have a light aluminum frame, but you've got a dense steel component, like a battery mount, welded to one side.
Okay, I can picture that.
The geometric center, the centroid, might be right in the middle of the overall frame shape.
Makes sense.
But the center of mass, and therefore the center of gravity, where the weight acts, that would shift significantly towards the heavier steel part.
Ah, okay. So it's not just some, academic technicality.
Not at all.
It's the difference between maybe a structure that stands strong and one that, buckles under stress because you didn't account for that weight shift.
Precisely. Especially when you're combining different materials, maybe advanced composites. It fundamentally redefines where engineers need to look for the true balance point of these hybrid designs.
So that distinction is vital for accurate analysis.
Absolutely vital.
Yeah.
It means that perceived balance point isn't always the geometric center if the material isn't, evenly distributed.
Okay. And at their heart, all these calculations, whether we're talking weight for G, mass for cm, or pure geometry for C, they fundamentally involve a balance of moments.
Right.
Can you unpack that moment idea a bit, like the seesaw example?
Yeah, the seesaw is a perfect analogy. Think about it. A small child sitting far from the pivot point,
The fulcrum.
right, the fulcrum,
Hmm.
they can balance a much heavier adult sitting closer to it. Why? Because of the turning effect, or moment they create. It's force times distance.
Okay.
So engineers essentially sum up these turning effects from every tiny part of an object to find its overall balance point, where all those moments balance out.
And that leads to a useful shortcut.
It does. A really key shortcut is that the centroid, C, will always lie on any axis of symmetry for the body.
Ah, okay. So if you have a perfectly symmetrical beam, like an I-beam,
Exactly. You already know its centroid has to be right along its center line, or center lines if it has multiple axes of symmetry.
that must save a lot of calculation time.
Significant computation time, absolutely.
Okay. But what happens when you're dealing with objects that aren't simple geometric shapes? Things like a custom-designed aerospace bracket, maybe?
Or a complex curved architectural element you see on some modern buildings.
Yeah. Engineers can't just look up a formula for those, right?
Not usually, no.
Yeah.
This is where precision engineering really turns to calculus, integration.
Ah, integration. So how does that work here?
Well, the basic idea is that when shapes get truly complex, engineers essentially slice the object, mathematically speaking, into tiny, infinitesimally small, manageable pieces, differential elements.
Like tiny strips or cubes?
Exactly.
Hey.
Could be a tiny line segment for a rod,
Hmm.
a thin rectangular strip for an area, a little disc for a volume. Depends on the problem.
Okay.
Then you figure out the moment arm for each tiny piece, its distance from some reference axis.
Right, it's contribution to the turning effect.
Precisely. And finally, you sum up the effects of all these tiny pieces across the entire shape using integration. Calculus lets you do that summation precisely.
Which gives you the total value, like total area or volume, and its effective location, the centroid.
Exactly. This method allows engineers to pinpoint the centroid for even the most intricate custom designs. And what's fascinating here, this isn't just for new, complex designs. It's also how we can mathematically prove some fundamental geometric truths.
Like what?
Like the fact that the centroid of any triangle, doesn't matter if it's equilateral, isosceles, scalene,
Any triangle at all.
is always located at exactly 1/3 of its height, measured up from its base.
Integration proves that.
Integration provides the rigorous mathematical proof. It's a fundamental truth revealed by this powerful technique.
That's pretty neat. Okay, so that makes perfect sense for these like custom, maybe organic shapes where you need calculus.
Yeah.
But what if the object you're analyzing isn't one smooth, continuous curve?
Right. What if it's a combination of several simpler shapes?
Yeah, like a machine part that's maybe made of a rectangle bolted to a triangle with a semicircular cutout.
Common scenario.
Do engineers have to resort to complex integration every single time for something like that?
Ah, good question. And the answer is absolutely not. That would be really inefficient.
Okay, so there's another way.
Yes. This is where the real ingenuity or maybe practicality comes in. Instead, they use what we call the composite body method.
Composite body.
You can effectively break down that complex object into a finite number of these simpler known parts. Parts you already know the properties of, like their area and centroid location.
Like the rectangle, the triangle, the semicircle we just mentioned.
Exactly, those basic shapes you find in tables and textbooks. Then, instead of integrating over the whole complex shape, you just sum the moments of each of those individual simpler parts to find the overall center of gravity or centroid.
So it's like discrete summation instead of continuous integration.
Precisely. It's much simpler computationally for these kinds of built-up shapes.
And here's where I think it gets really powerful, right? This method can even handle holes or empty spaces.
It can. That's one of the clever aspects. You simply treat a hole or a cutout as an additional composite part.
But it's empty.
Right. So you give it a negative weight, or a negative area, or a negative volume.
Ah. So you're effectively subtracting its influence from the whole calculation.
Exactly that. It's like subtracting that piece from the puzzle to find the balance point of just the remaining shape. Super useful.
Can you give a practical example of where that composite method shines?
Sure. Imagine designing a large water tank for a city. Maybe it's generally cylindrical but has a hemispherical bottom.
Okay.
And maybe there's a large pipe hole bored through its side for an outlet.
Right, a complex overall shape.
Definitely. Instead of trying to set up some nightmarish integration for that whole thing, you can conceptualize it as three simpler parts: a
Yeah.
cylinder, a hemisphere,
Both positive?
and a negative cylinder representing the whole.
Ah, okay.
You find the center of gravity and the volume or weight for each of those simple pieces individually. You can look those up or calculate them easily. Then you combine them using those simple summation formulas.
So you'd use this for real-world assemblies, like...
Absolutely. Determining the center of mass for an assembly made of, say, a conical frustum, joined to a hemisphere, even with a cylindrical hole bored through the middle. This composite approach makes calculations that would otherwise be really daunting, well, efficient and manageable.
allowing for faster, safer designs.
Exactly. It's a workhorse method in engineering.
Okay, so we have these methods to find the balance points. What does this all mean for practical applications in actual design and manufacturing?
Well, it means we can do some remarkably clever things. For instance, using the theorems of Pappus and Guldinus.
Pappus and Guldinus. Sounds historical.
It is. These are elegant theorems, first developed way back by Pappus of Alexandria in the 4th century A.D.
Wow.
and later restated by Paul Guldin. They provide an incredible shortcut, really, to calculate the surface area and volume of certain shapes.
What kind of shapes?
Specifically, bodies of revolution. These are objects formed by spinning a 2D shape around an axis.
Like spinning a rectangle to make a cylinder? Or a triangle to make a cone?
Precisely. Or a semicircle to make a sphere. These theorems are a beautiful testament to how sometimes abstract mathematical principles can unlock real-world efficiency. They let designers visualize and quantify complex structures much faster.
Okay, so what's the first theorem? You said surface area.
Yes, the first theorem is for surface area. It states that if you revolve a plane curve, like an arc or a line segment, around an axis that doesn't intersect it,
Okay.
the surface area generated is simply the product of the curve's length times the distance traveled by its centroid.
The centroid of the curve itself.
Yes, the centroid of the generating curve.
Huh. So if you know the curve length and where its balance point is...
And how far that balance point travels in a circle. Multiply them, and you get the surface area instantly.
That seems powerful. Where might you use that?
Well, think about estimating the amount of sheet metal needed for a storage building's big curved roof.
Like a Quonset hut style.
Could be.
Yeah.
Or maybe the precise surface area of a large circular seawall needed for coastal protection. This theorem gives you that quick, powerful shortcut. Saves a lot of time in material estimation and cost analysis.
Okay, and the second theorem? Volume.
Similar idea, but for volume. The second theorem says if you revolve a plane area like a rectangle, a triangle, a semicircle area around an axis that doesn't intersect it,
Right.
the volume generated is the product of that area times the distance traveled by its centroid.
So area times the distance its centroid travels.
Exactly.
Where would that be useful?
Well, this is exactly how you'd quickly calculate the volume of, say, fertilizer contained within a large silo if you know its cross-sectional shape.
Or the amount of concrete needed for a circular curb around a park.
Perfect example. And what's truly fascinating here is how these theorems can swiftly derive fundamental formulas you probably learned in school and maybe took for granted. We'll take a semicircle. If you revolve the semicircular arc around its diameter,
Okay, spinning the curved part.
using the first theorem, you quickly prove the surface area of the resulting sphere is 4r.
Just like that.
Just like that.
Okay.
And if you revolve the semicircular area around the diameter,
Spinning the flat area.
using the second theorem, you instantly get that the volume of the sphere is 43r.
Wow, okay, that is elegant. It shows how deeply interconnected these concepts, centroids, area, volume, revolution, really are.
It's a beautiful demonstration of their predictive power.
All right, so we've talked a lot about balancing objects, finding their geometric centers, but what about the invisible forces acting on them?
Ah, yes, loads.
Let's shift gears a bit and turn our attention to distributed loads and fluid pressure, because many real-world forces aren't just single concentrated points, are they?
No, definitely not. They're often distributed over a length or an area.
Like wind.
Exactly. Think about the constant pressure of wind pushing on the side of a tall building.
Or the immense weight of water pressing against a dam. That's not acting at one single point.
Correct, it's spread out. So for general distributed loading, you can often visualize it as a pressure diagram, maybe like a curve or shape over the surface.
Okay.
The magnitude of the total resultant force from that distributed load is actually equal to the total area or volume under that distributed loading diagram.
The area under the curve, basically.
Essentially, yes. And crucially, the line of action of this single equivalent resultant force, where does it act?
Let me guess. The centroid.
Exactly. It passes directly through the geometric center, the centroid, of that loading diagram's shape or volume.
Okay, that sounds incredibly important for structural design.
Absolutely vital. For example, calculating the resultant force from wind loading on a building's front or side walls and knowing where that force acts.
Is crucial for designing the frame, the columns, the bracing.
That holds the building together safely, ensuring it doesn't twist or worse, overturn.
Right. Now, let's talk specifically about fluid pressure. That's a common distributed load.
A very common and important one. Fluids at rest exert pressure according to Pascal's law.
Pascal's law. Remind me.
It says the pressure at a given point in a fluid at rest is the same in all directions. And, importantly, its magnitude increases predictably, linearly, with depth.
Deeper you go, the higher the pressure, like
Yeah.
diving in a pool.
Exactly. The formula is often written as P, where gamma is the specific weight of the fluid, and Z is the depth.
Okay, pressure increases with depth. So imagine a submerged plate, like a submarine's hull section or maybe a gate on a canal lock.
Mm-hmm.
The pressure on it isn't uniform then, right?
Correct. It's lower near the top surface of the fluid and higher down at the bottom edge of the plate.
So it creates this kind of triangular or maybe trapezoidal load distribution across the plate?
Precisely. A linearly varying load. And this concept applies directly to designing things like the walls of the storage tank. They have to be thicker or stronger at the bottom to handle that greater pressure.
Okay. And when a fluid exerts this varying force on a submerged surface, the total resultant force, does it act at the plate's geometric center, its centroid?
Not necessarily. This is a key point. The resultant force acts at a specific point called the center of pressure, often labeled P.
Center of pressure, P, different from C, the centroid.
Yes. And what's fascinating, or rather critical here, is that for a flat submerged plate, the center of pressure, P, typically does not coincide with the geometric centroid, C, of the plate itself.
Why not? Where is it usually?
It's usually located deeper than the centroid.
Deeper because...
Because the fluid pressure is higher further down, the bottom half of the load distribution is bigger than the top half. So it pulls the resultant force downwards from the geometric center.
Okay, that makes sense. But this raises an important question then. Why does this distinction between the centroid C and the center of pressure P matter so much?
It matters profoundly for stability. Because if you don't know the precise point of action for these significant fluid forces, your design could be dangerously unstable.
How so?
Think about a massive concrete dam again. Its stability against overturning, literally tipping over about its base,
Yeah.
depends entirely on the exact location of that huge resultant force from the water pressure. That force acts at the center of pressure, P, if you assumed it acted at the geometric center, C, of the dam's face.
Your stability calculations would be wrong. Potentially catastrophically wrong.
Exactly. Missing this distinction, miscalculating the center of pressure, could lead to failure.
Wow. Okay, so even for really complex shapes like curved dam faces or maybe flat plates with varying widths submerged in water.
Yes, even for those, engineers have sophisticated methods. Sometimes it involves integration again, or breaking the pressure load down into horizontal and vertical components to find the exact magnitude and the precise location of these resultant forces. They're literally mapping these invisible but critical forces.
It really underscores how vital getting these points right is.
It's fundamental to safe design.
So let's try to wrap this up. What does this all mean for you, listening? We've seen how these, well, seemingly abstract concepts, center of gravity G, center of mass Cm, the centroid C, center of pressure P.
They might sound academic at first.
Right, but they're actually the backbone of understanding stability, structural integrity, and just how objects behave under all sorts of forces. They're really the hidden language of balance that engineers have to speak fluently.
They provide that precise blueprint for safe, efficient engineering design. It doesn't matter if it's for a simple rod, a complex machine part, a massive water tank, or a continent-spanning bridge. Understanding these points is key.
Absolutely.
So, what stands out to you about how knowing an object's or maybe a force's balance point can fundamentally change the entire approach to tackling a design challenge? How it might perhaps turn a seemingly impossible engineering task into an elegant, achievable solution?
That's a great question to ponder. And maybe consider this. The next time you see a crane lifting an impossibly heavy load, seemingly with grace.
Or a dam holding back a vast reservoir.
Or even just a car smoothly turning a corner at speed. Remember that behind that successful, often quite mundane-looking operation lies a really precise understanding and calculation of these invisible balance points and force distributions.
It really is a fundamental insight that shapes and quite literally supports our world.
One precisely calculated center at a time.